everybody, so today we'll try to do an integral. So this is integral 0 to 1 x to the power n. So what you see here, this is called the fractional part of a number, any number. Here it's 1 by x. So I'm taking the fractional part and to the power n dx, right? So how do we do this particular integral? So this is the kind of integral which we are not used to, right? Just to remind you what fractional part means, so if I have fractional part of 3.14, this is nothing but 0.14, right? That's the fractional part of this particular number, right? Now, so how do we even go about solving this? So it's a nice little trick here. So first step will be to make a change of variables. So let's make this change of variables y to be 1 by x, right? So you have dy will be minus 1 by x squared dx. So that means dy will be just minus y squared dx, right? So with that, y to the power n, and this is the fractional part of y to the power n, and then I can do this. So dx is minus dy by y squared, right? So this is minus, let me put the minus here, minus dy, and then there is 1 by y squared. Now your limits change, right? So when you have x is 0, your y will be infinite. When your x is 1, your y will be 1, right? So let me make that change here. So infinite and then 1 here, and because there's a minus 1, so the limits get swapped. So you have 1 and infinite, the fractional part of y to the power n, and then you have divided by y n plus 2 and then dy, right? So this is the integral that we have. So let me write it here. So integral 1 to infinite, fractional part of y to the power n, y to the power minus n minus 2 dy. Okay, so that's the first step. Now how do we go about solving this further? So you can see here the integral is from 1 to infinite, so you can make it into a summation. And how do you make it into a summation? I'm going to break this integral into small integrals, right? I'm going to break the domain. So the domain of this integral is 1 and infinite. I'm going to partition this into smaller subintervals, right? So I'm going to write this is equal to integral k plus 1, and then there's fractional part of y to the power n, y to the power minus n minus 2 dy, and then k is 1 to infinite. See, I'm breaking this down into small intervals, so you can see this is 1, and then so 2, and then so it doesn't matter if it's open or closed interval, it doesn't matter. So 1, 2, and then I'm going to do 2, 3, and then 3, 4, right, and so on, right? I'm going to break this domain 1 infinite into these smaller subintervals, and so you can write the summation. You can split the integral as a summation format, right? Now, why did I do this? This makes the computation much simpler because I can do something about this fractional part, right? So to be precise, what's the fractional part of y? Fractional part of y is nothing but y minus the integer part of y, right? So y minus the integer part of y. For example, if you have 3.14, if you want the fractional part of 3.14, this is nothing but 3.14 minus the integer part, which is 3, so you get the fractional part, which is 0.14, right? So that's how you get the fractional part. So this is the formula here. So now using this, what will happen is summation k1 to infinite integral k plus 1. So the fractional part is y minus the integer part of y raised to n, y raised to n minus n minus 2 dy. Okay, so now if you look at this domain k and k plus 1, the integer part of y for any point lying in this domain, right, lying in this domain k plus 1, any number that lies here, the integer part will be k, right? The integer part will be k, right? So because the integer part is k, you can actually write this as this is okay, so this should be the integer part. So this is summation k1 till infinite integral k plus 1, and so this is y minus k to the power n, y raised to minus n minus 2 dy, right? So this is the integral that we get here, and now you can see this is pretty much solvable, right? This is something which we know how to deal with, right? Probably integration by parts. So let's do the integration by parts. So I'm just going to pick k plus 1, y minus k to the power n, y raised to minus n minus 2 dy, and so this will be, so when you do an integration by parts, what you get is, let's okay, so what we'll get is y minus k to the power n, and then you basically integrate this term here. So when you integrate this, this is y to the power minus n minus 1 divided by minus n minus 1, and you put the limits k plus 1, and then you put a minus sign, and then basically you have an integral, the same limits k plus 1. You have this term here, so this is y to the power minus n minus 1 divided by so there is minus n minus 1. So I'm just gonna do a plus here, and then I'm going to say n plus 1, and then this is y minus k to the power n. Basically you need to differentiate it, so let me write that part here. So when you differentiate it, you get n y minus k to the power n minus 1, and then you have dy, right? So let's break this down further. So you have okay, let's do this part. So when you evaluate the limits, you see that when you plug in y equal to k, this whole term will become 0. So only k plus 1 will yield a non-zero number here. So when you put k plus 1 here, so this is k plus 1 minus k to the power n, so k plus 1 to the power minus n minus 1 divided by minus n plus 1, and plus integral k plus 1. So let me pull this n and n plus 1 out. You have y minus k to the power n minus 1, and then y raised to minus n minus 1 dy. Right, so that's what you get. Now, what I'm going to do is, I'm going to simplify this further. So this is k plus 1 to the power, let me write this as follows. So minus 1 by n plus 1, k plus 1 to the power n plus 1, and then plus n divided by n plus 1, and then you have integral k plus 1, so y minus k to the power n minus 1, and then y raised to minus n minus 1 dy. Right. Now there's something interesting going on here. So if I go to this particular term here, this is where we started this integration by parts. So if you look at this, let's denote this as I, n, n, k, right? So n is for this exponent value n, and then k is this value here. So I n n k. Now if you go down, right, so this is the integration by part result, and what you see here is the same thing, right, but n minus 1, right, and then there's k. So if you just compare, right, these two are the same. Let me just, yeah. So if you look here, this is I n n k, and this is I n minus 1, n minus 1 k. Basically the integrals are the same, but just the exponent is n minus 1 here. Here it's n, right? So that's the difference. So we can write this in a recursive formula, right? So you get a recursive formula. What's the recursive formula here? I n n k is equal to minus 1 by n plus 1 k plus 1 to the power n plus 1 plus n divided by n plus 1 I n minus 1 n minus 1 and then k, right? So this is what we get. Let's do one thing. Let's just bring this n plus 1 to, let's multiply throughout by n plus 1. So you have I n n k is equal to minus 1 by k plus 1 to the power n plus 1, and you have n I n minus 1 n minus 1 k. Right, now what's the next step here? Let's make this n, right, as a variable I, right? So what you need to do is just make this I plus 1. I'm just changing the n to I, and you will see why I'm doing this. So let's make this all so I minus 1, and then k. Now what you can do is, actually you can see this. So if you compare these two, let's bring this to the left hand side. So you have I plus 1 I k minus I minus 1 I minus 1 k is equal to minus 1 by k plus 1 to the power I plus 1, right? So you see here these two quantities, right? It's giving you a recursive formula. So what you can do is you can sum them up, right? So if you can actually do a summation of this term from, let's say, I1 to n, right? So when you have the summation, when you do the summation, what you will see is that many of the terms will get cancelled, right? And you will get a nice looking formula for this n plus 1 I n n k, right? So you will see what I mean when I do this summation step here. So so when you sum this, right? So when you sum this from I equal to 1 to n, right? Let's denote this entire thing as star, right? So when you sum this star, right, you can see that many of the terms will get cancelled, and what's left is n plus 1 I n n k minus the, when you put 1, what you have is I 0 0 k, which we need to evaluate what it is, and this is equal to, so the right hand side, this is summation I1 to n 1 by k plus 1 I plus 1, right? So I0 0 k, actually you can go and convince yourself by doing this on your own. So remember, I n n k is this, right? This is the integral, right? So when you plug in n equal to 0, right, you are basically left with this kind of a integral. So integral k to k plus 1 y raised to minus 2 dy which, well, very easily can be evaluated. This is something like k plus 1, right? So you, or maybe there's a minus sign, so minus 1 by k plus 1, right? This is what you get. And so that's basically your I 0, 0, k, right? So using that, you can come down and you can actually replace it. Let's shorten this a little bit. So you can actually replace this term here. So this is n plus 1 I n n k minus, so it becomes plus 1 by k plus 1, because we found that this is nothing but minus 1 by k plus 1, so this is equal to minus summation I1 till n 1 by k plus 1 I plus 1, right? So that's neat. That's looking neat. Now, how will this help us, right? So let's look at this. So where did we start this whole thing? So we started here, where we had this, if you can see here, this is a summation, right? There's a summation, right? And then there's an integral, which is basically what we have evaluated. And what you have is this I, n, and k, right? You have a nice looking formula. So let me write it down. So I, n, and k is minus 1 by n plus 1, k into k plus 1, minus 1 by n plus 1, summation I1 to n, 1 by k plus 1 to the power I plus 1. Now, using the summation here, so the summation runs from k1 to infinite of this integral. This is basically I, n, and k, which we evaluated, right? So this is I subscript n, n, k, which we know what it is, right? That's basically what we have here, right? So summation k1 till infinite I, n, and k, right? This is summation k1 till infinite of this term. So this is minus 1 by n plus 1, k plus 1, and then minus 1 by n plus 1, summation I1 till n, 1 by k plus 1 to the power I plus 1. So, and remember, this whole thing is nothing but the integral, right? Integral 0 to 1, x to the power n, fractional part of x to the power n dx, right? So this is where we are left off, and let's see if we can solve this. Actually, this is solvable because it's a series, right? Which can be handled very easily, because what you're left with is minus 1 by n plus 1, summation k1 till infinite, 1 by k plus 1, and then you have minus 1 by n plus 1, summation k1 till infinite, summation I1 to n, 1 by k plus 1 to the power I plus 1. So there's a double summation here, which is quite interesting, but it can be handled pretty easily. So again, maybe I will leave this as for you to convince yourself that this particular summation actually is this can be broken down. The 1 by k plus 1 can be broken down as 1 by k minus 1 by k plus 1, right? So when you sum the series, many of the terms will get cancelled, and what you're left with is just 1, right? So the answer is 1. I'll leave it up to you guys to just go and verify this. And what you're left with is this double summation, which might look a little scary, but it can be handled well. All you need to do here is you have this minus 1 by n plus 1, minus 1 by n plus 1. Well, now you have this term here, right? Let's just swap this summation. So summation I1 till n, summation k1 till infinite, 1 by k plus 1 to the power I plus 1. So I need to justify why I can do this swapping, but you will see later that there's nothing wrong with doing this particular step here. Well, there are many theorems in math which tells you when you can swap this, when your series when your series is basically absolutely convergent, then you can definitely do this. Or maybe you can, if you have learned some measure theory, then you know from Fubini's theorem that you can swap integrals, and so basically the same thing for summation. But anyway, those are details. You don't need to for now you can just take this as a fact that you can swap this. If you can swap this, then let's see what we get. So you have minus 1 by n plus 1, minus 1 by n plus 1, and you have this thing here, so summation I1 to n. Well, this thing is interesting because it's the Riemann zeta function, right? It's the zeta function I plus 1, but maybe because this is starting from 1, so this is 1 by 2 to the power I plus 1, plus 1 by 3 to the power I plus 1, 1 by 4 to the power I plus 1, and so on. So you're left with that 1, right? 1 is missing, so you actually subtract 1. So what you're left with is this is nothing but the Riemann zeta function I plus 1 minus 1, right? So that's what you have here. Now, if you now you can see that this is just need a little bit more algebra here. So this is minus 1 by n plus 1, minus 1 by n plus 1, summation I1 to n, Riemann zeta function I plus 1, minus summation I1 to n, 1, and then you have 1 by n plus 1, right? So, well, this summation is nothing but n, right? This is nothing but n, so you can actually replace this by n. This is minus n, and so you combine these two, the first and the third term. What you're left with is minus 1 and minus 1 by n plus 1 summation I1 to n, Riemann zeta function I plus 1. Okay, probably I made a mistake somewhere. So minus and minus should be plus, and this shouldn't be a minus sign here. Probably I made a mistake somewhere here. So this summation, right? The summation will be there's somewhere I have made a mistake for sure. Okay, so I'm sorry. So the mistake is here. Well, my apologies, because this should be 1 by k times k plus 1, right? So when you do this integral, probably I should have done it on my own. Integral k to k plus 1 y to the power minus 2 dy. This should be 1 by k plus 1. So if you have that, well, if you go down, it's just a minor, the negative sign should change. So this so here it should be so when you scroll down, so this should be a minus sign here, right? So let me change that to a minus sign, and so when you take it to the right hand side, it should be a plus here. And now if you do the whole thing, you should get the correct answer. There should be plus here, plus here, plus here, and yeah, all of these terms, this should be plus, plus, and this one as well, it's a plus here, and so you are left with 1, right? So yeah, so that's 1 minus 1 by n plus 1 summation I1 to n Riemann zeta function I plus 1. So this is the final integral, right? So let me write down the final integral here. So integral 0 till 1 x to the power n fractional part of x to the power n dx is nothing but 1 minus 1 by n plus 1 summation I1 till n Riemann zeta function I plus 1, right? So this is what you get as the final answer. So what I will do is, in the next video, I'm gonna change this exponent. So this, I basically made this n, right? But you can basically evaluate this integral for p and q, where p and q are different, right? So you can still evaluate this integral and you will get different formulas. For now, I will just keep it n, right? Just the simplest case. But this turns out to be something interesting. This has the Riemann zeta function here. If you don't know what this is, I've done a video where I've evaluated the integral for Riemann zeta function, so you can go and check that out as well. But yeah, so this is what it looks like. Yeah, so a lot of computation, but finally we see something interesting, right? So let me make it smaller. Yeah, so this is what you have at the end. Okay, so I'll stop it here. We'll see you next time. Till then, take care and bye.